Dear students, and welcome once more to the GCE Math panel. This particular lesson this day is on partial fractions. And recall that this is the third chapter of our online preparations. For you to get the previous notes and previous lessons, please don't forget to go to our YouTube page, GCE Math Panel, or you can go to our site, gcemathpanel.com or www.gcemathpanel.blogspot.com. Let's take this lesson, and once more, welcome to the panel. So in today's lesson, we are looking at partial fractions. In the previous two lessons, we have looked at indices, logarithms, surds, absolute value equations, and absolute value inequalities, and the theory of quadratics. And today we are in chapter 3, which is on partial fractions. Partial fractions is made up of 4 cases, in which we have the case with linear factors in the denominator, repeated factor in the denominator, quadratic factors in the denominator, and in all of these 3 cases, the degree of the numerator is less than that of the denominator. And for the 4th case, the degree of the numerator is greater than or equal to that of the denominator. So those are the 4 cases which we are going to be looking at. And what is the importance of these partial fractions? It is very, very important when we'll be looking at series expansion and when we'll be doing integration. Stay tuned. And if you have not subscribed to this channel, please, to encourage our team, hit on the subscription button below. You can equally share and leave your comments so that we know how far we have gone and how much more we can assist. So for the first case, we have linear factors in the denominator. And what do we mean by a linear factor? In this particular partial fraction here, we have dx plus e in the first bracket, and in the second, we have gx plus h. These two are all factors, and for a factor to be linear, the highest power of the variable, in this case x, the highest power of x should be 1. You can just see x here, it means x to the power 1. So we say this first factor is linear, and for the second factor, it's also linear, because the highest power of x here is 1. So when a factor or a fraction is written like this, if you look at the degree of the numerator, it is 1, and the degree of the denominator is the highest power of x in this bracket, or the highest degree in this bracket, times the highest degree in this bracket. In that case, x to the power 1 times x to the power 1, which is x to the power 2, and the degree of the numerator here is less than that of the denominator, which is 2. So in this case, we can express this in partial fractions as follows. A constant over the first factor, that is capital A. Now in this case, this capital A is different from the small a, plus a constant over the over the second factor. So to express this in partial fractions with linear factors in the denominator, we have a constant over the first factor plus a constant on the second factor. Take note of this. Let's take an example. So to express 2 over x minus 1 into x plus 1 in partial fractions, this will be identical to a over the first factor x minus 1 plus b over the second factor. At this step, the next thing we have to do is to multiply all through by the denominator of the given equation. The denominator here is x minus 1 into x plus 1. So we multiply term by term on both sides of this identity by this denominator, or call it denominator of the given equation, or LCM. So we multiply term by this LCM. On the left-hand side, we will be left with 2. On the right-hand side, we will have a over x minus 1 times this LCM will be left with a into x plus 1, and b over x plus 1 times this denominator will be left with b into x minus 1. From this step, we can solve for these constants a and b by equating coefficients or by the cover-up method. We are going to look at all of these 2 methods. So we start by equating coefficients. Let's look at it in the case of equating coefficients. So if we expand, we will have 2 is identical to ax plus a plus bx minus b. We bring like terms together. Ax plus bx, the same like a plus b, all of that in brackets, x outside. And a and minus b are constants in another bracket. So at this point, you can equate coefficients. In this case, A minus B is a constant on the right-hand side. The only constant on the left-hand side is 2. So in this case, A minus B is equal to this constant 2, because since this is an equation, constant on the left-hand side should be equal to constant on the right-hand side, and variables should be the same. Now looking at this equation 2, A plus BX is a variable or a term with an unknown, but there is no term on the left-hand side an unknown. So this term has a corresponding value of 0 on the left-hand side. So this term should be equal to 0. And we can form two equations. So A minus B is this 2. Constant is equal to constant. And this one, since there is no x on the left-hand side, then A plus B should be equal to 0. These are the two equations, which we can solve by elimination, by adding the two equations. We have 2a equals 2, thus a equals 1. And substituting a equals 1 into any of the equations, we have b to be equal to minus 1. Therefore, we can write this function f of x equals this in partial fractions as f of x equals a is 1 over x minus 1, plus b, b is minus 1. So I can write plus minus 1 here as just minus 1 on x plus 1. So this has been expressed in partial fractions. If you are asked to express this as a single fraction, you now look for the LCM of this and simplify. It will bring you back to this equation. So in this particular example, we have used the method of equating coefficients, and not on paper 2, we mostly have these equations existing or seen as equations 1 or 2 and so on. And at integrations, at times, we are required to apply this principle before we integrate. Take note. Let's take another example, but before we take those examples, we have numerous exercises on the right-hand side. This case, you have to understand that you have to first of all factorize this one. You have x plus 1 into x minus 1, since it's a difference of 2 squares. This is a quadratic, yes. It's not linear, but when factorized, it becomes linear. So you have to factorize first, the denominator here. And the same thing here, you have to factorize. Let's take the next example. We have f of x equals x 2 over x squared minus 1. To express this in partial fractions, the truth is that this case is a linear case. But somebody will say that the highest power of x here is x to the power 2. How can I be saying that it's linear? Yes, you are right. However, I'm right too, because this is linear because it can be written as x plus 1 into x minus 1, since it's a difference of 2 squares. So this now be identical to a over the first factor. You can see I've written it on the right, bottom right. A over the first factor, which is x minus 1, plus b over the second, which is x plus 1. The next step is to multiply term by this LCM, which is x minus 1 into x plus 1. And when we multiply, on the left-hand side, you'll be left with 2, is identical to that. If you look critically, you'll see that this same example is the same as the previous example. Because in the previous example, you have x minus 1 to x plus 1. Now they have expanded, and you can start as a difference of 2 squares. So at this point, you can equally equate coefficients. We expand, bring like terms together. Constant is equal to constant. Therefore, a minus b equals 2. Variable equals variable. Therefore, a plus bx is equal to 0. And when we solve, you have the same results that we had on the previous page. You can see that these two examples are the same. It's just the same question. Now, let's take a second example. Since these two examples are the same thing, let's take a second example now. We have to express 5x minus 3 on x plus 1 plus x, into x plus 3 in partial fractions. This is a past question of 2016. So this is identical to a over the first factor plus b over the second factor. You are in an examination class. Please do not watch this video with your eyes. After watching, make sure you also solve with your hand. Because if you just watch, then you are not gaining the question answering skills. Do not just watch. You must watch and solve. So the second step here is to multiply term by this LCM. And on the left-hand side, you'll be left with 5x minus 3 to be equal to, I rather use identical to, when you multiply a over x plus 1 by this LCM, we'll be left with a into x plus 3. When we do the same for b over x plus 3, we are left with b into x plus 1. In this example, I like to use the cover-up method. Cover-up method is like elimination. Something disappears, another one appears. And for the cover-up method, we will look at the factors that we have in this denominator. We have x plus 1 as a factor and x plus 3 as a factor. So in this case, we equate each to 0, solve for x, and we say let x be this and let x be that. Let's see what we do here. I'll start with this first factor, x plus 3, for the cover-up method. I'll say let this x plus 3 be equal to 0. When I solve for x, x will be equal to minus 3. So in this equation now, what happens when x is equal to the minus 3? You have equated this one to 0. When x equals minus 3, and you substitute in this equation, you have 5 into minus 3, which is minus 15 minus 3 minus 18. This is the minus 18 here. It's identical to, when you replace x here by minus 3, this term will disappear. So we say it has been eliminated or it has been covered up. We cover it up. So this is the cover-up method. When something disappears, we call it cover-up. It's actually some sort of elimination. So now, in this case, where we have a minus 3 plus 1 here, will give us minus 3 plus 1 is minus 2 times b minus 2. So at the end, we are left with minus 18 is equal to minus 2b's, and solving for b gives us 9. Now, what happens when x is equal to minus 1? Why minus 1? I've equated x plus 1 to 0 and solved for x. So when x is equal to minus 1, we will have 5 into minus 1 is minus 5 minus 3 minus 8. This is the minus 8 here. It's identical to on the right-hand side. This term is covered up, or this term disappears. Minus 1 plus 1 is 0 times b 0. So when we fit minus 1 here, we'll have minus 1 plus 3 giving us minus 2 times a. Gives us 2, rather plus 2 times a. That gives us 2a's. And our a here is equal to minus 4. Note, you may still decide to use other numbers like 0, minus 1, 2, minus 2, but this number should be very close to 0, so they don't have a cumbersome expressions to simplify. So you can now replace these values on the right-hand side of this expression of the linear case, and we will have f of x to be equal to a is minus 4 over the first factor, that's x plus 1, plus b, which is 9 on x plus 3. So this is the case of linear factors in the denominator. Linear factors in the denominator. All right, guys, let's take another example. You can leave your comments below. Don't forget to subscribe, to like the videos, and to share them. Thank you in advance. So we are required to express the polynomial, or call it into partial fractions, x minus 1 over x plus 2 into x plus 1. So they want us to decompose this into partial fractions. So we notice that in this case, we have linear factors in the denominator. Linear factors means the highest power of x for each factor is 1, as you can see. So this is identical to a over the first factor plus b over the second factor. We multiply all through by the LCM, we'll be left with x minus 1 is identical to a into x plus 1 plus b into x plus 2 by cover up, or we can equate coefficients and solve, bringing like terms together here. Ax plus bx is equal to x. So a plus b is equal to 1, because this one x is the same as 1x. And equally, a plus 2b is here. It's a constant, it should be equal to this constant minus 1. So when we solve a and b by elimination, we have a to be minus 1 and b to be minus 2. And finally, we have a to be 1 and b minus 2, rather. Expressing this in partial fractions gives us 1 over x plus 2 minus, b is negative 2, that's why we are putting minus here, because this is plus minus 2 over x plus 1. All right, another example, you have 3 minus x over x squared minus 1. So the first thing to notice here is that this is a difference of 2 squares, and we can write this as x minus 1 into x plus 1, such that we have it in partial fractions in this form. And multiply all through by the denominator, this is what we are going to have. And by cover up or by equating coefficients, A will be 1 and B minus 2. And in partial fractions, you will have this to be identical to 1 over x minus 1 minus 2 over x plus 1. This is another example. We follow the same procedure. And these are the results for A and B we will have. But I want to lay emphasis on something here. What happens when the values of A and B are fractions? If there are fractions, the results, the final answer can be written in 2 ways. This is what I want you to note in this question. Take note. So this can be written as A, which is a half. You just write a half at that position, and B, which is minus a half at that position. But this can equally be written like this. For the fraction, you take the denominator down. So you have 1 over 2. This denominator here is moved to the denominator of the fraction itself, of the overall fraction. So you have 1 over, but you must now put brackets here. You must put brackets. 1 over 2. Can you see? Now minus, this one is a half. So I'll write minus 1 and bring down this denominator, 2 into x plus 1. So be very, very careful when the values of A and B are constant. It can be written like this. So this brings us to the second case. In the first case, we had repeated factors, linear factors in the denominator, and the degree of the numerator is less than that of the denominator. In this second case, this is case 2 or type 2 as they call it. This one can be type 3 in some books. We have repeated factors in the denominator. What I want you to understand is what we mean by repeated factors. What is a repeated factor? A repeated factor is any factor that is raised to a power. For example, you have x plus b to the power 2 here. This is a repeated factor, which means this x plus b will normally appear in partial fractions 2 times. The factor is going to be repeated somehow. So for me to express this in partial fractions, this x plus a here is linear. So we don't have an issue with this x plus a. It's going to maintain its form like in the previous example or case 1. But our concern here is this x plus b to the power 2. So in partial fraction, I'll write this as follows. A over this linear factor plus b over this repeated factor, firstly to the power 1, then secondly, c over this repeated factor to the power 2. If it was the power 3, I'll continue with d over this repeated factor to the power 3, and so on. So it can be written like this. A over the first factor, it is linear. So this one, we have no problem. Now plus b, this factor is raised to the power 2. So over this factor to the power 1, or you just write the factor like that. Since the factor is raised to the power 2, we'll continue on to n at the power 2. So plus c over x plus b to the power 2. So if it was the power 3, we'll continue with plus d over x plus b to the power 3, and so on. Let's take an example on this one. So express x plus 1 over x minus 2 all squared in partial fractions. So this is a summary of this form here. So here we have a repeated factor. So with a repeated factor, please you can talk with me. This will be identical to a over this factor to the power 1 plus b over this factor to the power 2. There is no linear case here, so we skip this linear part. This gives us a over x minus 1, that's to the power 1, plus b over x minus 1 to the power 2. So from this step, I'll mostly be using the cover-up method. So when we multiply all through by this LCM, that's x minus 1 to the power 2, term by term. On the left-hand side, we'll be left with x plus 1. It's identical to a over x minus 1 times x minus 1 squared. That will give us a into x minus 1. Now plus b, the factors will cancel out here. Now, using the cover-up method, I'll equate this x minus 1 to 0 and solve for x. So if x is equal to 1, x equal to 1, we substitute here, we'll have 1 plus 1, 2, be identical to 1 minus 1 is 0. So this a disappears, or we have covered up a, and we are left with b. So b is equal to 2. Now, somebody said now there is no other factor. What do we do? what we are going to do, we are going to use any other number that is very close to 0. We can use any number that is even bigger than 0, there's no problem, but let's use numbers very close to 0 or 0 itself, so that we avoid cumbersome simplifications. So for example, now start, what happens if x is equal to 0, for example? If x is equal to 0, I have 0 plus 1, which is 1, will be identical to 0 minus 1 minus 1 plus a, minus 1 times a rather, minus a plus b. So this gives me this equation, but I already know that my b is equal to 2. Since b is already equal to 2, I'll have 1 is equal to minus a plus 2. And when I solve for a there, it will give me a value of 1. So to express this in partial fractions, I'll have a, which is 1 over x minus 1, plus b, which is 2 over x minus 1, all squared. If you look for the LCM and bring this back together, you will have the same equation that has been given. Another example we have, to express x minus 1, these are exercises for you to do. X minus 1 over x plus 1 into x minus 2 all squared in partial fractions. So as you can see here, this is a linear factor. So I'm just going to have a over this linear factor. This one is a repeated factor. So plus b over this repeated factor to the power 1 plus c over this repeated factor to the power 2. At this point, we'll now multiply all through by this LCM or by the denominator of this equation. On the left hand side, we'll be left with x minus 1 is identical to a into x minus 2 all squared plus b into x minus 1 into x minus 2 plus c into x plus 1. So using a cover-up method, if x is equal to 2, 2 minus 1 here is 1. This will be identical to 2 minus 2 is 0, so a disappears or is eliminated, or we have covered up a. And now with b, if I fit 2 here, all of this term will disappear because 0 times all of this is 0. So you're left just with c. And since x is 2, 2 plus 1 is 3. 3 times c is 3 c's. So we'll have 1 to be equal to 3 c's. This implies that c is equal to 1/3. Now, if x is equal to minus 1, the minus 1 is coming from one of these factors. When you equate x plus 1 to 0, you substitute x equals minus 1 in all of this, you will have minus 2 to be equal to 9a's. And from here, a is equal to minus 2 on 9. Now you can use another number very close to 0 or 0 itself, since I have not used it. If x is equal to 0 or use x equals 1, anything, you will have the same results at the end. If x equals 0, we substitute all through, we will have minus 1 on the right hand side. On the left hand side is equal to 4a's minus 2b's plus c on the right hand side. But we know the values of a and c. We substitute these values in this equation to have the value of b. So at this point, our b will be equal to 4a's plus c's plus 1 on 2. So that will give us 4a plus c plus 1 on 2. We substitute the values and we will have 2 over 9 as the value of b. Therefore, in partial fractions, we can write this as a over x plus 1, where a is minus 2 on 9. You can write the minus 2 on 9 at this position, or you can write the minus 2 above and bring down the 9 and open brackets. A b is 2 on 9. You write the 2 above and the 9 below, or you can write everything as numerators. And a c is 1/3. If you don't understand the concept, you can rewind, you can go back and play this video again. Go to our blog, you'll get the notes equally and follow them if you have issues with data, and that will just be okay. Then the next example, so we have x minus 2 all over x squared plus into x plus 1. The first thing you have to note here is that the repeated factor here is x to the power 2. They can write the repeated factor before or after. It's x to the power 2. Because normally we know that it's supposed to be x plus something to the power n. But here that constant is 0. So you just have x to the power 2. Therefore, you can write this as a over this repeated factor to the power 1. Or you can decide and start this linear factor. So you have a over this repeated factor to the power 1. Plus b over this repeated factor to the power 2. We end now at 2 because the factor is raised to the power 2. now plus c over this linear factor. We now multiply all through by this LCM. We will be left on the left-hand side with x minus 2. And this is what we have on the right-hand side. Ax into x plus 1 plus b into x plus 1 plus c x squared. Now, using the cover-up method, if x, or when x equals minus 1, our c will be minus 3. If x equals 0 and we substitute, we will have b to be minus 2. And if x equals 1 and we substitute the values of b and c in that equation, then our value of a will be 3. Make sure you solve these equations again. Don't just watch. Solve them. Mathematics is drill and practice. Don't forget this. For your exams, you need the knowledge skills and you also need the writing skills. Without the writing skills, you're wasting your time. So you can conveniently express this in partial fractions as 3 over x minus 2 over x squared minus 3 over x plus 1. So here are some examples on the left-hand side of your board, the left-hand side of the board. Please take these examples, solve these examples. This brings us to case 3, non-linear factors in the denominator or quadratic factors in the denominator. We have seen the case of linear factors in the denominator, repeated factors in the denominator, and now we have quadratic factors in the denominator. And what is a quadratic factor? A quadratic factor in the denominator is that factor which you cannot factorize. And with quadratic factors, we assume, or because in partial fractions here at pure maths, we don't need complex factors. That is factors that have complex numbers. So this x squared, if you look at x plus a here, is a linear factor. We don't have, that's not our concern. X plus b is a linear factor. That's not our focus. X squared plus c, this is the alma mater. Because this is a non-linear factor or a quadratic factor. It's a quadratic factor because I cannot factorize this. But if I had x squared minus c, then I can break this down into x minus root c into x plus root c, a difference of 2 squares. But this is a sum. So this therefore leaves us no choice than working with this quadratic factor. So with the normal case, I'll have a over this first factor because it's linear, b over this second factor because it's linear, but we are going to do some modification with this quadratic factor, and this is what we will have. So for the quadratic factor, we will have its numerator of the form cx plus d. That's capital C x plus d, where this capital C is different from this small c. Please don't forget that. Let's take an example. So this is the summary of this case below here. The summary of the case below. So let's take an example. We have to express this polynomial f of x equals that in partial fractions. And we notice that we have a quadratic factor x squared plus 3. If you have something like x squared minus 3, we can say that this can be written as x minus root 3 into x plus root 3. But here it is positive, so it's a quadratic factor. So this will be identical to a over this first factor plus bx plus c over this quadratic factor. We follow the same procedure for the previous questions. And on the left-hand side, multiply all through by this LCM, we are left with 3x plus 4 to be identical to a into x squared plus 3 plus bx plus c into x minus 1. When x is equal to 1, and we substitute all through, we have 7 is equal to 4a, and a is equal to 7 on 4. Now, if x is equal to 0, because I cannot use this, so I cannot solve this one. If I equate this to 0 and solve, I will have x to be equal to plus or minus I root 3, which is a complex number. And that is a further complex number, so we don't need that here. So this will finally give us the value of c to be equal to 5 on 4. So we now have to look for b. We say, for example, if x is equal to minus 1, we can solve for c. We know that the values of a and c are 7 on 4 and 5 on 4 respectively. So when we substitute that in this equation and solve, we will have our b to be equal to minus 7 on 4. So this can be written in partial fractions as a over the first factor. A is 7 on 4. You can just write 7 on 4 as numerator, or you can bring down the 4 like this, as I explained earlier on. Now plus bx plus c. With bx plus c, our b is negative 7 on 4. This is it, minus 7x on 4. I can put it at this position because I don't want it to be affected by signs. Then plus c, as c is 5. So I'm running away from sign issues. If I put this negative here, it might affect this result. And I'm running away from the effects of negative signs. So be careful with this. So 5 minus 7x is the same as minus 7x on 4. But I can put this plus here and put that in brackets, minus 7x on 4. Or I can put a minus here and put 7x, and this is going to affect these other results here. So we have to be very careful with this. That's why I've swapped the positions like this. Nothing has changed in the equation. Let's take another example with these repeated factors. You can follow our classes online by going to the blog, and you will see the password and the student ID key. And you can join us from anywhere just by looking at the time of the class. This is another example, and the quadratic factor here is x squared plus 1. So this is identical to a over x plus 1 plus bx plus c over x squared plus 1. Multiplying all through by the denominator gives us 2x minus 1 on the left-hand side. It's identical to a on the right-hand side into x squared plus 1 plus bx plus c into x plus 1. When x equals minus 1, we have a to be minus 3 on 2 when we substitute. You must solve this exercise again. Otherwise, you are just reading and not studying. There's a difference. Now, if x is equal to 0 and we substitute all through, we have c to be equal to a half. And if x equals 1 and we substitute, the value of b will be equal to 3 on 2. Value of b will be 3 on 2. So in partial fractions, we have this as a, which is minus 3 on 2, minus 3 on 2 is x minus 1 plus b. Our b is 3 on 2. So we have 3x on 2 and plus c. Our c is a half. So I can conveniently write this one like this because all the denominators here are 2. The denominator of the b is 2 and that of c is 2 because I have 3 on 2 and 1 on 2. So I can write like this. Otherwise, I'll have to write everything as the numerator. So on the left-hand side, we have some examples. Please take these examples. Make sure you solve these exercises. Solve them. So the last case occurs when the degree of the numerator is greater than or equal to the degree of the denominator. When this happens, we have to do what we call long division. That's the first step. And when we do that long division, we have a quotient, which can be a function depending on the value of p of the degree of p of x and that of q of x. If the degrees are the same, then a g of x will be a constant. But if this degree is higher than this one, then this degree will be a variable. So plus whatever is left to express that one now in partial fractions. This might not be understood very well except after taking an example. Let's take an example. Express x squared over x minus 1 to x minus 2 in partial fractions. The degree of the numerator here is x to the power 2, or it is 2, and the degree of the denominator is highest degree in this bracket times highest degree in this bracket. The highest degree is x to the power 1. The term with the highest degree is x to the power 1 also. So x to the power 1 times x to the power is x to the power 2. So in this case, the degree of the numerator and that of the denominator are the same. So we do long division. We expand the denominator first before we do long division. And we will have the denominator, when we expand, we'll have x squared minus 3x plus 2. So x squared divided by all of this. Now for long division, take note. The next lesson is on polynomials and long division. You will understand this there better. And they're also looking at factor and remainder theorems and identities. So x squared, highest degree divided by highest degree, that's where we start. Highest degree divided by highest degree, x squared divided by x squared gives us 1. Now 1 times all of these divisor, 1 times x squared minus 3x plus 2 gives us x squared. 1 times minus 3x minus 3x, and 1 times plus 2 is plus 2. We now subtract. Normally we don't write the subtraction sign, but we are subtracting this from this. So we have x squared minus x squared, 0, and 0 minus 3x is plus 3x, plus 3x, and 0 minus this constant minus plus 2 is minus 2. Now that this degree is less than the degree of this divisor, we stop, can no more divide, because 3x divided by x squared, the degree is going to be less. If you have something like x squared here, we'll continue. So this is where we stop. So in partial fractions, this one can now be written as f of x is equal to this quotient, which is 1, now plus the remainder. The remainder is 3x minus 2. All that on this denominator in the equation. So we have 1 plus this remainder, all this on this denominator, x minus 1 into x minus 2. And this is what we have. Okay, so now we will just focus and express this in partial fraction. When you have the final answer, we come and replace it at this position. So in partial fractions, this will be identical to, these are all linear factors. Normally, when we divide like this, we can have any of the other 3 cases, and we now express in partial fractions. So this is identical to a over the first factor over b over the second factor. And when we do all of that and express in partial fractions, we are going to have the values of a and b respectively to be minus 1 and 4. We now write this equation in partial fractions as follows. F of x is equal to 1. This 1, start this 1 here. Now plus, we continue at this position, these partial fractions, plus the value of a is minus 1, so I write plus minus 1 over this first factor x minus 1 plus b over x minus 2. So in partial fractions, this is what you have, this 1 here, then minus or 1 from here plus, I now consider this position. A, which is minus 1 over x minus 1 plus b, which is 4 over x minus 2. Let's take the last examples. Express 2x squared over x squared minus 1 in partial fractions. Here the degree of the numerator is 2, that of the denominator is 2. So we do partial fractions, long division. So we have 2x squared divided by x squared minus 1. 2x squared divided by x squared is 2. 2 times x squared minus 1 is 2x squared minus 1, minus 2 rather. We now subtract, we have 2x squared minus 2x squared 0. 0 minus minus 2 is plus 2. In partial fractions, we will have this quotient 2 plus the remainder 2 over x squared minus 1. So we just focus on expressing this one in partial fractions. But we have done this one before, so we can just copy the answer and put here. When you did it before, this was what you obtained. All right, and let me just play the video to go. The values of a and b were 1 and minus 1 respectively. So in partial fractions, this one will be written as 2. Then we continue from here. Plus 1 over x minus 1 minus 1 over x plus 1. So we have expressed this in partial fractions. Here are other examples. Make sure you solve these examples. With this particular case, the third one, the degree of the denominator is x times x to the power 2, which is x to the power 3. So x to the power 4 divided by x to the power 3 is x. So we expect this divisor or this numerator here to be something like ax plus b. That's what you expect it to be. So we equally have some past questions to express in partial fractions. Make sure you answer all of these questions, guys. And if you have not clicked on that subscription button below, do it now. If you have not shared this video with your friends, share this video now and leave your comments below. If the comments you have, leave the comments below this video. Here are some past questions which we have put. Our next lesson is on polynomials. At the end of every month, we have an exam which students have to take. You just have to go to the blog and you enter your number and you take the quiz. It's online and you submit and it is marked in 1 day and you see your results. It is free, and don't forget to share this with other people and friends to encourage workers in our platform to produce more for you. Equally on our blog, we have other subjects, not just mathematics. We have physics, chemistry, and so on, which are being integrated into the process. Stay tuned, stay well, eat well, study well, sleep well, rest well, and meet you in the next class. Bye-bye.